So good morning, students. Today, this video we will be actually working on Lstm, which is a very popular algorithm even until today, right? So we'll be coding and we'll be basically using some data sets so that we can learn the Lstm, how to apply Lstm to data sets. So we already covered Lstm in our class, but I can quickly recap, right? That is the input to Lstm is the input itself, the previous hidden state, and the previous C cell state. Actually, it should be T-1 right here, both of them. And then the output is basically the next hidden state and the next cell state, right? I guess if you try to make sense of this, it's very difficult, right? And if you take a look at this, it's actually very, very simple at Lstm. So we have these three gates: input gate, forget gate, and output gate, and all of them are applying sigmoid, right? In which it turns the value here into 0 to 1, right? Two numbers from 0 to 1, right? So in a nutshell, they are all numbers from 0 to 1, right? So when they are multiplied with some number, they are basically serving as like a mass, right? That can turn things on and off, right? So that's why they are called gate, right? Output gate, forget gate, and input gate. And they're simply finding some linear combination of the input and the previous hidden states and try to find a way to define this something called input gate, right? And then we have this GT, which is basically taking all of this, the current input and the previous hidden state, and applying some activation function, and then you get GT, right? You may wonder why not ReLU, right? Because at that time, Lstm is proposed in 1999, and at that time, the 10 is still very popular, right? So once you get GT, you can see that the stale state is simply for the forget gate multiply, right? This is Hardeman product. So, but Hardeman product just means directly multiplying, right? With the previous cell state and plus with the input gate multiplied with the GT, right? That would define the cell state, right? And then the relationship within the hidden state and the cell state is simply that hidden state is basically taking the output gate multiplied with some squeeze version of the CT, right? But once you understand the IT, FT, and OT are basically a linear combination of XT and HT, and somehow we just try to have HT. So basically, by having so many routes, right, to reach HT, there are so many ways that to prevent from vanishing and exploding, basically vanishing gradients, right? Also, it has so many routes such that it allows CT to keep information, right? No, so maybe IT has a so you can see that because CT depends on CT-1 and also GT, right? But there's also FT and IT that controls how the information flows. So there's so many ways that previous information can be preserved, right? That's why Lstm works better than on-end, right? So that is the intuition, right? But I don't want you to feel very scared of this. But anyway, today we'll be coding a little bit. A quick note that if you guys are interested in the coding Lstm from scratch, I also have one here in my GitHub. So feel free to take a look. But I guess yeah, they are very easy to look at. So feel free to go into. But in my tutorial this time, I will be simply using Lstm that is provided by PyTorch, and then try to apply on some data sets. All right, so today we'll be loading data sets, doing some EDA, simple EDA, tokenization, numericalization. We'll be using FastStick embeddings. So in the previous tutorial, I am focusing on training our own embeddings, right? Which requires a lot of CPU and GPU power, right? So in industry, if you don't care about getting the state of the art performance, etc., I think it makes sense to just download the embeddings that people already train on millions of tokens, right? And one is that one popular one is fast-tick embeddings, which is basically like word to vec, but it's based on subword and character base. Yeah. And then we're gonna have data loader for batching, model training, and tests. All right, great. So let us first import some stuff. So we're gonna first import, I guess, torch data, torch text, right? And I think let me just select my kernel. All right, and I don't like this, right? So I can open it again, and then that comment should be gone. Great. And then import torch.nn as nn, right? Right, and this is for those who watch my video maybe 2 or 3 years from now. Now I'm recording in 2023 December, so if you watch this like in the future, then you want to maybe fix your version. I mean, you can use your latest version, but you may probably need to fix some part of my code, right? All right. So those are my version, and definitely you can also use GPU. I'm currently coding on my MacBook Pro, so I don't think I have, but you can always check, right? So you can see that it's false. For those who are using GPU, you can do like this, right? Device equal to torch.device, CUDA, if this one is available, otherwise CPU, right? And then you can, of course, take a look at this device. And of course, if your device is, you have your device, you can also take a look at torch.cuda.get device name, right? That would probably give you maybe the first device, and you will see your CUDA name, your device name. For myself, I don't have a device, so big errors is strong. All right, so I think that should be it, right? And then the next thing I want to make sure that I have is the seed, right? And what is seed, right? Seed is basically a number, a hash number, I guess, that is used to randomize, like for example, the data loaders, right? What got into training or data testing set, right? So by specifying a seed, you can always get the same results, right? But the idea is that for your research papers, right, you want to maybe run this. You may want to change 3 times, right, and run the whole Jupyter notebook or Python file and then average the results, right? Because certain seed may get you lucky on the training and the testing set, right? So this is a very important practice that you all must do for your research papers. All right, and of course, this should be also help us make sure we are that. Okay, great. So now that once we figure out everything now, so that we can now start loading our data sets. So here I'm gonna use, by the way, I'm not sure this is big enough, so I'm gonna make it slightly big. And we're gonna use torch text data sets. In the future, we're gonna play more with like CSV file, with actual data sets, but for now, let us stick with the built-in data set. So, but if you know how to manipulate CSV into such kind of data sets, I think this is the same. Right. So this is basically classifying 4 types of news. into right into, I guess, I'm not sure, let me check. I think is something like business something. Give me 1 second. It's world news, sports, business, and technology, right? So that is the label is 1, 2, 3, 4, etc. All right. And so we can take a look at train, and this is basically a data type, a data pipe data set, very similar to PyTorch data set, like tensor data set, right? But just more efficient because they are built in with generators, so they don't load everything immediately. So we can definitely so that is just loading data sets, right? So we can club here, and now we can do some EDA, right? So we can do, right? So you can see that. So what I'm trying to do is turn the training set into iterator, and then I just call next, which will give me the first. And if you type next again, it will give me. I think it will just give me the next one. But here, I think. Okay. Anyway, so here is 3, and probably belonging to. I think there are 4 types of news, right? So 3 is probably the business, right? And this is the news, all right? And then we can also take a look at the y. So we can say iter less, right? And it will give me for y, x, and this, right? I only want the y, and use the common list comprehension, right? And you can see that we got 4 labels right here. Of course, we can also take a look at the training sets. So we can do iter train and list and length, I guess. And you can see that the train size is 120,000, right? In this tutorial, I will not be training and try to get the best accuracy because it's just gonna burn my MacBook. But just to demonstrate you like the basic flow of how to analyze data. So here I'm just gonna make everything. I'm just gonna make everything much smaller. So I'm gonna say train dot random split. Yep. And I'm gonna say total length is train size. And I'm not sure I can enter here, but let me try. Weights equal to weights equal to dictionary, and too much. The first one is basically 0.7, and train is 0.2, and then valid is 0.1. Great. And I think it should be comma if I'm not wrong here. Okay, great. And then okay, I'm missing the seed, right? So I can comma here and say seed equal to seed. Okay. Great. So now we have randomly split this, so we can now take the trained size. Right. Okay, great. So I think we would. I think this is iterator, right? So we need to do some. We need to again do some iter list again, and then now we do length, right? Yep. And then that is 24,000, and I think we can do the same for tests. I mean, valid. and that is 12,000, right? Of course, you guys can split for testing, but we're gonna stick with training and validation set. Great. So I think that should be it. So now we just do simple EDA, but of course, what you want to do is probably try to do some statistics, whether there's this is a balanced data set. What are the common tokens? What are the average number of tokens, right, in each of the news, right? That would be probably what I would do, right? But I will leave that to your assignments, perhaps. So I'm going to close this, right? And then now we're going to do the tokenization, right? In my previous class, what I did is simply split according to words, right? But right here, I can introduce SpaCy, right? So make sure you install SpaCy, right? But here I'm just gonna, and of course you have to make sure you install SpaCy like this, right? But of course, it depends on whether, right? This is basically the tokenizer. This SpaCy inside this has a English tokenizer, and I'm using a small version of this SpaCy, right? But of course, I will have one dedicated class that teaches SpaCy, right? But for now, make sure you have SpaCy, all right? Okay, so now once you have everything, now we can do from torch text dot data dot utils, import get tokenizer, and then the tokenizer, okay, tokenizer, right? So I'm defining tokenizer, get tokenizer SpaCy, right? So I'm gonna use the default, and the language is basically Anchor web system, right? If you don't have this in your system, there will be error, right? And we can actually demonstrate a little bit, right? So we can say tokenizer, we are currently learning Lstm in YouTube, right? So that would be probably something. And you guys can actually now print out the tokens, right? Great. And now you can see that everything is split very nicely, okay? And that should be good. We have some warnings, but I guess this is probably related to how torch text handles SpaCy, probably. Yeah, every time you see a warning, you should take a look and see whether you can fix this. But since we are using all the libraries, we have no control to how they use this. Yep. Okay, great. So now we have defined the tokenizer, and so I think we are done with this. We're gonna later on use this tokenizer, right? For splitting our data sets. All right, now we can do this numericalization again. In the previous tutorial, I have performed vocabs using the very manual way, right? But this time again, I'm going to use torch text to help me do this. I mean, this is the whole thing, right? I try to teach you like from the manual way and try to slowly incorporate API and libraries so that you can understand from the basic until the advanced one without losing any granularity. All right, so then we can have, so we have this function called build vocab from iterator, and so basically it requires some kind of iterator, and then it would just read the vocab and build vocab accordingly. So firstly, I need to I need to create a function that give me the iterator, so that, and then I can call this guy and send in this function for it. And then it's a for text and data iter yield tokenizer and text, right? So then it will just give me each of the text in the data iter. So what I'm gonna do is the vocab equal to build vocab from iterator and say yield tokens. And then here we can just pass in the training set, right? And then it would just be iterating. I guess this is a label, right? And we want the text, right? And then comma, we can say specials equal to unc. And I think I need to make this smaller. Pan. Beginning of sentence. It does not need to be like this, by the way. But we just try to create new symbols and then add to this vocab, right? So if I'm not wrong, the vocab will just assign this as 0, 1, 2, 3, and then the rest of them will be starting from 4. And then I'm gonna say vocab dot set default index to be vocab unc. All right. So now it's reading a lot of text, and now you can actually take a look, right? And this vocab is amazing. You can pass in, for example, here it is, right? And then you can get the corresponding number for each of them, right? Definitely, you can also map everything back using some function call. So we're gonna say mapping equal to vocab dot get itos, right? And then we'll just say mapping 532, right? And that is here, right? And we can actually try 0. That is unc 1, 2, 3. I'm not really sure you can pass in like this, right? And I know, so it must be integers, right? So that is what it is. Okay, great. So now we got this, right? And we may want to also check what is the length of the vocab. And that is 52,000. All right. So I think that is tokenization and numericalization. If I'm going too quickly, you feel free to just pause the video or maybe go to my GitHub. All right. All right. So the next step is trying to prepare the FastTech embeddings, which will be incorporated inside probably the model or the data loader, right? We will see. So we're gonna just use torch text again, and which has this FastTech already supported. By the way, you don't have to necessarily use torch text. FastTech is not by torch text, is by someone else. So you can manually download that embedding, or you can also load like this, right? And I think today we may able to see how we can actually load the embedding inside the model. All right, and then we can say fast vectors equal to fast text, language equal to simple. All right, so I'm just gonna pause a little bit my video, and then I will come back when it's finished downloading. All right, so I have finished downloading, and then now based on this, I can actually I can do something like this: fast vectors dot get vex by tokens vocab dot get itos. So by doing this, I can actually get all the vectors of the tokens inside of my vocab, right? And then I want to make sure that I always put this in my GPU if I have. If not, it should be in CPU, right? And then fast embedding. All right. So we can actually check a look at this shape. So in total, we have so you can see, check here, right? So we have length of vocab, and we have a total of 52,000 vocabs, and each of them is mapped to fast text embedding of size 300, right? So for example, if we want to, okay, so let's say maybe I'm interested in some word, then maybe maybe I want to take a look at the embedding of Ankh, right? So that would be how it looks like for Ankh, and then okay, they all look like this, right? So now we got number 4, which is not actually special tokens, and now we have some unique numbers that we don't understand, but it's already trained, right? And if you wonder what is this for, then you can take a look at the vocab and try to take a look what is this number 4, right? All right, so I think we got this fast embedding, and later on we're going to learn how to actually add this embedding to the neural network, which will be very useful technique. All right, so now we are done with the fast text embedding. Now we can prepare the data loaders. So firstly, I have to create the text pipeline, which is a simple function, right? That take input called X, tokenize it, and apply the numericalization, and which turns it into number, right? So this one turned it into word, and this one turned it into numbers, right? So that is my text pipeline, and then my label pipeline. Right. This one will be used in my data loader collate function, which will be used inside the data loader again. And then because my labels start at 1, 2, 3, 4, I want it to start at 0, 1, 2, 3. Right. So what I'm gonna do is say lambda x, whatever that is incoming. I want to take that x and then -1. So this will basically turn 1, 2, 3, 4 into 0, 1, 2, 3. Yep. For those who don't understand this one, this is basically hello world. This is YouTube, right? You're gonna turn it into first. It's gonna turn it into hello world. This is okay. This is getting along. YouTube, and then it's just gonna turn it into again numbers, right? So it's gonna be. I'm not sure. Like I don't know the numbers, right? Right. So that like that would be probably the example of this pipeline. All right, so then of course we can apply and then take a look how this text pipeline. So I am currently teaching Lstm, and you can see that it maps nicely to a token, and we don't have this word Lstm in my fast text embedding, so it's Ankh. Of course, we can also take a look at my label pipeline, and if I put it inside some number like 3, it will give me 2. All right. Based on that, we're gonna create a collate function, which is a collate function. Although it looks very special, the name is very threatening. It's basically a function that takes the input, apply some transformation, and then put them into the batch, right? So that is basically what this collate function is. So what I'm gonna do is from porch.utils.data import data loader, right? Previously we don't have to use the data loader, right? Because we are doing everything from scratch, but you can always use data loader to make your life easier. And here I'm also gonna use path sequence, right? And what path sequence is basically is that, for example, if you have maybe in the first example, maybe the length of the sentence is like this, right? And the second example, the length of sentence may be, I'm not sure, like that, right? But if you want to put it into the same batch, you have to make sure that the sequence length are the same. Otherwise, the Lstm will cannot do this in batch, right? So what do? Well, you put padding, right? You put padding so that they are all of equal length, and this is exactly what this pad sequence is, right? It will pad based on the longest sequence in that batch. All right, so that is pad sequence, and then we can of course need to define the pad index a little bit. Vocab pad, right, which we already defined earlier, and then now we are able to create this function, collate function. All right, and we're gonna say label list, text list, length list equal to. All right, and then for label text in batch, right? So every batch there will be y and text. What we're gonna do is we're gonna say label list dot append and label pipeline label, right? So now we have this label list, and we're gonna say process text equal to torch.tensor text pipeline text d type equal to torch dot int 64, right? Because these are all numbers. This is not yet embedding. So, and I think I'm not missing any brackets, I hope. And then we're going to say text list append process text. The next one is a length list. The length is needed for you later on. We're going to use something called padded sequence, and that one requires some information of the length. So I'm going to say process text dot sign 0, and then finally we're going to return for every batch. It will return torch.tensor label list c type torch.n64, and then we're going to also return the text, and we're going to pad it. So text list, and then padding value equal to pad idx, and then okay, this is getting very long, and then batch first equal to true, right? And then I think okay, give me 1 second, I will be back. I'm not sure I'm missing anything. Let me take a look at this. All right, and then okay, I guess this is correct. So batch first is equal to true. Basically, by default, your data will be the batch will be the first, will be the second item. But here, when I say batch first equal to true, the batch dimension will be always the first. We're gonna take a look when we're actually running, and you will understand this batch first. This is optional actually. And then lastly, we need torch.tensor length list, and I think we need this d type to make sure everything is in integers. Okay, great. All right. So if I'm typing too quickly, you can always pause my video and go back and forth, right? Great. So using this collate function, now we can create our data loaders and put this collate function inside a column. So we're going to say batch size equal to 64 for no reason. Any number is fine. as long as your GPU can hold it. Train loader equal to data loader train, and I'm gonna say batch size equal to batch size, and shuffle equal to true, and then collate function is basically this collate batch. All right, and similarly, we're gonna do the same for okay, and this is the validation loader, and this is the test loader, and to align it together nicely. And this is a valid, and this is tests, right? And make a space bar so that it looks very nice. Actually, you don't have to shuffle tests and also validation, simply because shuffling won't actually make the model much better, because you just try to test the accuracy, right? So in that case, you don't have to really shuffle here. In fact, yeah, I guess that should be it. And then I'm not sure, you may want to put num workers so that you can run this faster. But I'm not going to do anything because I'm training on my MacBook, so actually I cannot train very heavily. Okay, so that is my that, and now I can actually run it and take a look, right? And I think so it can return me the label, text, and link, and train loader, right, and break. And once we have that, now we can actually so when I run this and I break, I already have this label in my system. So I'm gonna say label.shape, right? And this is basically, so we can remember, right, that the shape is basically batch size. And then we also have text.shape, right? And now we have batch size, and then this is a sequence length, right? And so I think if we don't use batch size first equal to true, it will be sequence length comma batch size. And of course, we can also take a look at sequence. We're gonna have link dot shape, and this is also 64, right? So I'm gonna take note of this. All right. So please remember this shape, and which will be useful when we design the model. All right. So I think this is done. A little bit too long because previously we manually do this, but now we are using a lot of torch text, so a lot to get used to it. Okay, but anyway, it's not so difficult. All right, so now the next step we can do is actually designing the model, and I guess this is the part that we're gonna learn quite a lot. And so firstly, we're gonna import torch dot nn as nn. By the way, before I even talk about this Lstm, I just wanted to let you guys know that Lstm is very powerful and it works even today. But given the large language models arrival, basically Lstm is less relevant nowadays. But still, by learning how to actually design your own model, Lstm, and in the future transformer, you can come up with your own network that may be even more powerful, right? So that is the idea. All right, so we're gonna say that, right? And we always have to create two functions. And sorry for it. All right, so those are the two functions we always have to work on. So firstly, what I'm gonna do is stripper Lstm self dot and then we're gonna say self dot embedding equal to nn.embedding input dim embed dim, and then heading IDX equal to pad IDX, right? And so we need this input dim. Input dim is basically vocab size, right? Embedding is that. Sometimes I change to vocab embed size, but please make sure that they are the same, right? So this will be the thing that holds the embedding, right? And then we will eventually set the embedding to fast text embedding outside of this, right? So we don't really have to train from scratch. Yep. But we're not gonna froze it, by the way. We're gonna just keep training, right? So some of the fast text embedding will be changed a little bit, yep, based on our training. So now we're gonna define our Lstm, and we're gonna say n.lstm, right? So there's a lot of things we're gonna talk about here. So we need to specify the embed dim, the dim, num layers equal to num layers, and then the bidirectional equal to bidirectional, and dropout equal to dropout. Yep, this dropout is basically the dropout from the first layer to the second layer. Yep. So if you have only one layer, it doesn't work. It doesn't mean anything. But I guess we're gonna have a lot of layers. But firstly, let me make sure we have all these parameters. Yeah, in some editors, if you just have some command, it would just pop into this constructor. All right, so now we have this Lstm. Now we can also send it some fully connected, and let's say nn.linear hit them times 2. The reason why I know is times 2 is because of this bidirectional. And then output dim. Right, and output dim is trying to predict all the possible. I guess if we want to classify 4 types of news, then probably the output dim should be 4, if I'm not wrong. Okay, so that is I'm not sure I can punch enter here, and it will hopefully not be it still work. Yep. Now we can work on the forward function, and so in the forward function we take in the text and the length, right? We don't need to take in the label, because the label will be used during the training. So here we're gonna just say, so the text, and when it come, right, it will be batch size sequence length, right? So it's always good to take note to keep you sane and not insane. And then we're gonna say embedded equal to self.embedding text, right? So, and then after this, we're gonna have text equal to batch size sequence length and embed size, embed dim, yep, which is 400. Yep. And then we're going to use something called pack sequence. So this is not pad sequence, this is pack sequence, right? And what it does is basically making sure that your Lstm will ignore any padding, right? So it's highly recommended you do this. Otherwise, your Lstm will learn so many junk, because it will consider the padding as something, right? So it's highly recommended. Yep. So pack sequence embedded equal to nn.utils .rnn .pack added sequence And I'm going to make this smaller, embedded text length dot CPU, right? And then what else? It needs enforce sorted equal to false, and right here is there should be something called batch first equal to true. Okay, so after it pack, the batch first is still first. Yep. All right, so it's a little bit long here, so I'm not sure I can enter here, and okay, that should make things a little easier. And then so by doing this now, if once the Lstm read this, it would know that it has to ignore all those paddings. Okay, and so now what we can do is we can take output length. I'm sorry. We have to insert it into Lstm. So we're going to say self.lstm pack embedded, right? And then you will get two things from Lstm, right? So firstly is the pack output, right? And the next one is HN CN, right? So here, if you read the documentation, right? Output is basically all the hidden states, right, stacked together. But HN is only the last hidden state, right? Same for the CN, which is the last self state, right? Right. So the one thing you have to know that once you pack, this HN will be the last HN will be the one that is without padding. But for this output, the last hidden state is still for the padding, right? So if you try to take the last one of this and last one of this and equal, they will not be equal, right? So that would be something you have to be very careful. What we want is using this one, which is a last hidden state that does not count the padding. Yep. All right, so now we have that. Now we can unpack it, right? So now we can say nn.utils .nn.pad pack sequence. All right, so this is a pack pattern. Now we're gonna pack, all right, which is basically like unpack. So we're gonna say pack output, comma batch first equal to true, and this one is basically the output lengths. Right. Of course, we're not gonna use anything about this, but this is I just want to write this line of code so that you know that if you really want to use this guy, which contains all the hidden states, including the padding, this is the way that you can actually extract from that pack thing to something that you can actually use. But in our case, what we're going to do is, but before anything, let us type the shape. So the shape is a batch size, sequence length, and hidden dim times num directions. All right. So if you have two direction, then you will have two of this, right? And then right here, your hidden, your HN is num layers multiply with num directions, and then batch size, and hit them, right? And similarly for the cell, that is also the shape, right? So we are currently writing the shape for output, right? So this output is basically has a sequence length of, so basically it contains all the hidden states for all the sequence length, and but it's only contained for the last layer, right? So that's why it has this hidden dim times num directions. But for HN, it has last hidden states of each layer, right? And of course, for each layer, if you have two direction, then you have that number of HN, right? So for example, if you have three layers by direction, then you will have HN1, HN1 forward, right? HN1 backward, forward and backward, right? And then you also have HN2 forward, HN2 backward, and then you also have HN3 forward and HN3 backward, right? So when I say forward means that it reads from the left to right, and that is the last hidden state. For the backward, I mean it reads from the right to the left, and that is the last hidden state, right? For the first layer, right? Usually, what you want to probably use is this two, right? Which is containing like the last layer and the last you want to concatenate those two things, right? So because of that, what we're going to do is the real last hidden state, like last layer hidden last layer last hidden states. All right, I mean this can be very long, but I'm gonna just make it HN is equal to taking torch.cat, and what I'm gonna do is HN the -2 and also the HN -1, right? And the dimension should be 1. All right. Great. So okay, we don't need this, right? So by taking the second last and -1, we're gonna have this one, right? Which we then concatenate them, and we're gonna concatenate them across in the batch size dimension, right? So that it will be stacked as that. And then finally, okay. I have to make sure that because this is I say batch size batch first equal to true. I think this one should be in the beginning. Yep. Sorry. All right. And so I guess when I put dim equal to 1, I'm actually concatenating these two together, right? Okay. So now once I have concatenated them, now the shape is simply batch size, right? Hidden dim times num directions. All right. So I think that is good now. And finally, we returned self.fchf. All right. Give me 1 second to take a look whether I'm getting the shape correctly. All right, and I will be back. Yep. All right. So I'm wondering whether when I put batch first here, would it be batch first here? Let me just take. We can always take a look at nn.lstm, right? And then try to take a look what does it return for the HN. This gonna take yep. So H will be always that, right? Even though even though you say batch first, this will always be the first, right? Okay. And okay, this is the documentations. So HT. Yep. So HN is the direction multiply num layers, and then the batch size, and then the hidden size, right? Yep. So I think it does not influence by that. So this is correct. I'm sorry again. And then also right here, right? And then if so, then that is correct, right? Because we are taking the last two of this guy, and for concatenation, we are concatenating across the dimension in which they are the same, right? Which is 1. And then once we do that, this dimension is gone, because we just select -2 and -1. And then we got batch size, comma, hidden dim times num directions. Okay, great. Okay, great. So now I think we are good to go. All right. Hidden dim is basically one of this, and num direction is basically backward and forward. All right. So once we figure out everything, now we can actually run this, right? All right. And if there's any problem, probably later on we're going to find. All right, great. So now with this finished, we can club this, and we can now move forward to training. So for training, we can firstly introduce something called weight initialization. Basically, the idea is that if you don't do this, it would just randomly initialize the weights and may reach convergence late. Like it does not reach convergence early. So by initializing weight, you can reach convergence much faster, according to the theory, right? So what I'm gonna say is that for each of this layer that belongs to nn dot linear, I'm gonna just simply use nn dot init Xavier. This is a very and I'm gonna put underscore, which meant in place, m dot weight. And I was also gonna do the same for the bias dot zeros, m dot bias, right? This is proven theory that if you apply this Xavier normalization, which is basically try to club all the weights within the normal distribution, is better for a linear layer in the beginning. And if the layer of Lstm, what we're gonna do is we're gonna for name param and m dot name parameters. Okay, we're gonna say if bias in name, we're gonna use nn dot init zeros param, and otherwise weight that in name. Then we're gonna use orthogonal, right? And there's a lot of theories you can take a look in, which proves that orthogonal weight initialization is quite beneficial, especially for Lstm. All right, so now we have the initialization. Now we can actually initialize the model. So we're gonna say input dim equal to length of vocab, set dim 56, embed dim. We're gonna stick with 300 simply because fast text is this, and then output dim is 4 because we have 4 types of news. Now we're gonna have num layers. We're gonna have 2 layers for no reason, which is bidirectional equal to true. and dropout will be 0.5, right? What this dropout is applied from layer 1 to the layer 2, not on layer 1, all right? And then we're going to say model Lstm, and we'll have a bunch of numbers, right? So I'm going to just copy my model. All right, and then put it right here and see what I miss. All right, everything looks good. Now we're going to say model.apply initialize weight, right? This will actually apply our weight function and make sure every weight is and we're going to also do for the embedding, right? So we're going to say embedding dot weight dot data equal to fast embedding, right? So by doing that, we initialize the weight, and we also make sure that the embedding does not start from scratch, right? It's going to start from the fast embedding, and then it will keep in fine tuning according to this data set. Of course, we can write some function for counting parameters. This is actually very optional, right? And so we're going to say params equal to p.normal, which will basically make everything into a long list, and model.parameters. If p dot response dot right, okay. And then what I'm going to do is for items and params. Actually, we just need to. Actually, we don't need to print each layer. I think it takes too much time. We're just going to say print sum of params. All right, and then we're going to say put this one in call parameters model. Right, and this model is I don't know how much this is. This is 18 million, right? So that is the size of our model, right? And now we can import torch.optim as optim. I mean, this is probably the first tutorial that I'm gonna code as much as this, but then in the future tutorial, we can reuse all this code, which will significantly shorten the future tutorial. Optimizer equal to optim.adam model.parameters li equal to 010. Okay, I already have li, right? Good. 1. Okay, and then the criterion is equal to nn.cross entropy loss. All right, and then so that should be it. And then now you can accuracy, that's y, and predicted equal to torch.max predicts.data. This is something we already did last time, right? So I'm going to go fairly quickly. I'm going to say batch correctness is basically predicted for every predicted equal to y dot sum, and then accuracy is basically equal to batch correct divided by length of y, and then we're going to return x. All right. So we have a lot of functions we already developed. Now I think we are ready to actually create functions for the train, right? So I'm gonna you can speed up my YouTube videos here, but I'm gonna just quickly tabulate it. I'm not gonna explain too much because they are mostly very self-explanatory. right? So this is my loader, right? And then firstly, I put it into my device. And then I'm gonna do predictions equal to model text length. Right. This is what my model requires, right? And then the squeeze one, right? So the okay, and then loss is equal to criterion predictions label act is equal to accuracy predictions label. All right, and then of course now we backprop. So we're gonna do optimizer dot zero grad loss dot backward, and then optimizer dot step, and finally we're gonna have some epoch loss to keep track of things. Loss dot item, and then the epoch act dot item. And now what we're gonna return in this function is basically epoch loss divided by loader length, and then the epoch act divided by loader length. All right. So this is a very simple function for training, and we're gonna do the same for. We're gonna just copy this, and then we're gonna create one more, and we're gonna call this evaluate. All right, and this is gonna take. It does not require the optimizer, obviously, because it does not need to optimize. And then this one will be eval. All right, and what we need here is with torch dot no grad. All right, to make sure that things run without any gradient to make things very fast. And then we're gonna we're gonna delete basically the backprop, right? We don't really need this. And yep, I think that's it for the evaluate. So enter. Again, if I'm going too quickly, you can always pause my video and type accordingly. Yep. So now we can actual training, right? Putting everything together. I think it should be 3. Right. So now we're gonna say train loader length. Train loader length equal to length list feature train loader. All right. Okay. So I think my name is valid loader. Okay, right. And if so, then I should change this to that. And now we have this. This will be used when we actually run this one, because we need this loader line. Okay, and we have some epoch function time. We can do start time, end time, and elapsed time equal to end time minus start time. Right. This is you don't really have to code this. This is not really necessary, but once you have one function, it's always good. I think you remember what I teach you guys in the machine learning course, right? In which I taught you ML flow, right? If you use ML flow, I don't think you guys need this kind of thing. Sex equal to end elapsed time minus you need to multiply minutes with 60. Yep, I think I'm not wrong. Yep, and then return elapsed minutes and elapsed seconds. All right. So once we have this, now we can actually code the actual training. All right. Best valid loss equal to float infinity, right, in the beginning, so it doesn't early stop. Now epochs. Let's say 1. I don't have let's say 2, right? I don't have CPU and GPU to run this, so it's going to take a lot of time. But if you want to save pod equal to f models, let me just take a look. Let me quickly create folders called models right here. Models, and I'm gonna say model dot class dot name, I guess. Dot pt. All right, so that would probably give me something like Lstm, something like that. Of course, you can put some timestamp here to make it even more unique. Now we're gonna say train losses equal to that. Train x val losses val x equal to, okay. Now we're gonna say for epoch in range num epochs. Okay. And here we need to simply say start time equal to time.time, right? And I think I did not import time, right? So I have to import time somewhere. So the time. And then I'm gonna say train loss, train act equal to train, and we need to have a bunch of things for the, so we need to send in the train loader, optimizer, criterion, and that train loader length, right? Similarly, we need this for valid. So I'm going to say valid validation, right? And this is should be well loader, and this should be well loader length. I think that is good. And once we have that, now we can do some plotting. Train losses. By the way, this video is getting long. You can speed up the video, and because most of this is already obvious, actually. Append train X valid losses dot append well losses dot append valid loss and val X dot append valid X. All right, so that is for plotting, and then we're going to say end time equal to time.time. And then finally, we're going to say epoch mints involve epoch 6 equal to epoch time, start time, and end time. All right. And now we're gonna have some early stopping here. Early stopping here. If validation loss is less than best valid loss, right? Then you keep on making sure that best valid loss equal to valid loss, right? And then also save that model, right? So that we can make sure that model.static. The static is basically giving you all the parameters number and then provide a set file. You can also then, you can say else break this whole loop, right? But I'm not going to do that. I'm just going to keep running it. And then in the case, I'm going to have a better model. All right. And now we're going to print long thing. So the epoch +1. And then time epoch minutes and epoch seconds. Yep, I think that should give me good numbers. And then of course I can print the train loss. I'm gonna put some tabs here. Train loss. Train loss. 3F. That should give me a nice and then train ACK. Times 100. 2F. All right. I think, and I'm going to put a percentage because this is a percentage. All right. And I can do the same for basically validation 2. So I'm going to val loss. And this one should be val loss. Right? Loss. And then val ACK. Valid ACK. Okay, great. So I think we can zoom out a little bit, and we have create this training function. It does not need to be this comprehensive, but this will be the only tutorial I do this. And then next time we're just gonna scroll through. So let us try to clear all the outputs, restart and run all from the beginning, and let's see whether this one runs. All right, so it's running from the top. Okay, it's now here, and things looks good here, and here is getting the link, elapsed time, and I got some errors. Lengths must be sorted, and when okay, so I think I must turn this to false. Yep. So enforce sorted. Okay, should be it's actually false, right? Okay, which function I'm length, right? Okay, give me 1 second. I will be back and I try to sort this out, all right? Okay, so right here it said you can pass enforce sorted equal to false to path a sequence, right? So I think maybe that can help me. So let me come up, and I think that this one enforce all right. So, but this one doesn't have this thing, right? Okay. Give me just 1 second, and we're gonna figure this out. All right. So I figure out the problems, right? So in here, actually I should have not this one, because Boolean is basically not a string, right? Okay, great. So that is a small mistake we did. So if we run this, it should work fine now, right? So let us run this, restart and run all. Right, and so now it's running, so I'm gonna pause my video, and once it's finished I will be back. All right, see you guys. All right, so now I'm already training for 5 minutes, and to no avail. Nothing is happening, simply because if you guys are training on CPU, it will just take a very long time, right? To save your time and my time, I would just show you guys what would be the actual results, right? So you can see that in the actual results, I'm using a GPU, and my validation accuracy is actually quite good, right? This is the best scenario, right? When the validation accuracy and training accuracy is very close, right? Meaning that we are not overfitting, right? And right here, I'm drawing some loss curve and also the accuracy curve. And right here, I'm just loading my model and try to evaluate on test set. And this is the testing accuracy. Finally, if you want to test on some random news, now you can actually, so what you have to do is, so firstly, you have to take your test string, apply the text pipeline, turn it into tensor, put it into device, and then actually make it as a list like this, right? And of course, now you have to reshape it into one to make sure that the first dimension is batch size, and definitely make the text length into according to the text size of the dimension one, which is how long is this sentence. 0 is the batch size, 1 is the length, right? So now you have the text shape. Make sure your shape of the text is batch size and the length. Now you just simply put the text and the length. And now you can see that once I input that, it predicts 2, right? I'm not sure what I actually, so this is Google is now following nonstop. And it's predicting 2, which is basically business, right? But if it's correct, then it should be actually 3, right? Which is the technology. All right. So now we can go back to our file here, and it's still running. But I think we can just wrap up everything and of what we have done today. So today we have go through this LSTM, and we walked on the data sets on news, and we do some EDA tokenization, numericalization here, and we learn to use plastic embeddings. We prepare some data loaders, and we design the LSTM layer, right? And we perform some training, and we actually test on some random news. All right. So thank you very much, and see you next time. Bye-bye.